Good morning, professors. I'm Aloysius with Team 24 here to start off showing to you guys our project. As you know, in nursing homes, feeding syringes are commonly found. However, they are usually reused to up to 5 to 6 times a day. It was discovered that washing and drying process of the syringe are ineffective and time-consuming, with an average of 2 hours 7 minutes per syringe just to complete this whole process. One of the few reasons why that is so is due to the allocated area for our nurses to dry the syringe. It is congested and mainly they rely on air drying the syringe, and washing of the syringe takes up another portion of the time, and due to each nurses have different methods of how they choose to wash the syringe. This is why my team and I decided that we would come up with an effective and efficient way to wash, dry and sterilize feeding syringe. So moving on to what we have found. So based on what we have found out, currently there are a few types of cleaners that can be found in the market. However, they are either made for industrial size washers, or nurses would still have to manually wash and dry the syringe before even putting them in for sterilizing. One of the few examples, as you can see on the screen, is a UV sterilizer that can be found online. Despite this machine being compact and able to sterilize and dry whatever is placed into it, it is unable to wash the item, and it costs more than $300 just for this one particular machine. So before I go into further details of what my team has come up with to tackle our challenge, we have came up with 3 factors that we can use to determine what a clean syringe should look like. And first and foremost is no visible residue should be seen. Secondly, there should not be any visible moisture. And last but not least, the transparency of the syringe barrel. Now I will hand over my time to Clement to tell you guys more about our product design.
Based on the background information, we came up with a list of custom requirements or the demanded quality. Next, these are the specific function requirements based on the custom requirements, and those in bold are the constraints from our customer. Take note that the width has to be less than 60 cm so that the product can fit on the countertop. These information are then put into the Quality Function Deployment Matrix, the QFD matrix. From the matrix, we identified the product design specifications based on the top few functional requirements with high relative weightage. This is shown circled in red. Therefore, these are the product design specifications. Subsequently, from the voice of customer, we came up with a few methods on how to solve what the customer wants. High pressure water and ultrasonic cleaning to wash, fan drying, spin drying and heating element to dry, steam and UV to sterilize. With these methods in mind, a few concept designs were developed. For the first concept sketch, its key features is that it uses high pressure water and rotation to clean, UV light to sterilize, and fan to dry. For the second concept sketch, it uses ultrasonic cleaning to clean, rotation, UV light and fan to sterilize and dry at the same time. For the third concept sketch, it uses ultrasonic cleaning to clean as well, but however it uses steam to sterilize and a heating element and fan to dry. For concept sketch 4, the last concept sketch, it uses ultrasonic cleaning to clean, UV light to sterilize and fan to dry. The advantages and disadvantages of the washing and sterilization method was found. From the analysis done, we were able to do the concept scoring and selection. The fourth concept was selected because it has the highest score. Concept design 4 was further developed after the selection matrix. Firstly, the orientation of the syringes have changed to maximize the space constraints. Next, a syringe holder was designed to prevent syringes from floating up when the syringes are placed in the water. It is also angled at a 10 degrees angle to help water droplets to flow down. This is to aid the drying process. This is the flowchart for our product, and this is the CAD model with dimensions. As you can see, the width is less than 60 cm, therefore it is able to fit on most countertops. There are many components in our model. I'll explain the purpose and functionalities of the key components in the next few slides. Firstly, the door is sealed to prevent ultraviolet rays from escaping. The material of choice is aluminium as it is lightweight and it has a high reflectivity for UV. Next, the display panel is touch enabled and it has a smart and user-friendly user interface. Next, the temperature and humidity sensor is used to gather data to determine if the syringes are dry. Also, the smart camera is there to perform machine learning and camera vision to ensure clean and dry syringes. There's also an electromagnetic latch lock to ensure that the door is locked when the machine is in operation. This is to prevent ultraviolet rays from escaping. Next, the enclosure is also made of aluminium material as it is lightweight and has high reflectivity for UV. Next is the UVC light to sterilize the syringes, as well as the ultrasonic tank, which is made of stainless steel material as it is durable and is corrosion resistant. The syringe holder is there to prevent syringes from floating in the water. It is also placed at a 10 degrees angle to aid in the drying process. Next, a lead screw mechanism is used to translate rotational motion to linear motion. The benefits of it is that it is compact in size, it is precise, accurate, and has a smooth motion. Next, the fan is located at the back because it will not be affected by the surrounding at the back. Next, the air duct transports air from the fan directly to the syringes. The outlet of the air duct is placed at the base of the syringe to facilitate the drying process. Next, the water inflow is connected to a solenoid valve to control the water inflow. As well as the water outflow, there's a solenoid valve as well to control the water outflow. When the valve is closed, the ultrasonic tank will fill up with water. Next, the electrical outlet. The wire is connected here to provide power to the machine. As well as the ultrasonic transducer. The transducer is used to generate ultrasound energy to the ultrasonic tank. It is mounted on at the bottom of the tank by adhesive. Next is the syringes. It's placed at a 10 degrees angle to aid in the drying process as seen over here. As well as the location for electronic components will be in these two red boxes. This is the exploded view for our model. The image on the right is a close-up version of the image for the image on the left. The features of our product is that it can automatically clean, dry and sterilize up to 8 syringes within an hour. It is smart and has a friendly user interface and it is safe to operate. Some of the prototyping that we have done is that we have 3D printed the syringe holder and test whether it can fit with the syringe and the plunger. We have also did some testing and verification to see the entire process. Through the testing and verification, some of the improvements we would like to see is firstly, to redesign the door to open from the top instead. This is to improve the ergonomics when placing the syringe into the machine. Next, to reposition the UVC lights to the walls of the enclosure. Also, to reposition fans to the top instead of the bottom at the back. This is to improve the airflow over here. Next, the air duct to be repositioned in accordance to the fan as well. And also, to redesign air ducts to transport air supply directly to each syringe as well. Lastly, the placement of the syringes may trap air due to the 10 degrees angle. Some of the possible solutions is to redesign either the syringe holder or the water inlet system to remove the air trapped. Further testing has to be done.
Thank you, Clement. Firstly, I will talk about the electrical component selection. It will be separated to component for washing, drying, and sterilizing, as well as other essential components. Component for washing includes a motor to control the lead screw movement, and a liquid pump to pump water in, and a valve is used to keep the water in and drain the water at the later process. An ultrasonic cleaner is then used for removing impurities. Such impurities includes food and fluid stuck on the syringe. For component used for drying includes USB fans to fasten the drying process and also LED light for camera module to see the syringe. The component for sterilizing is LED light strip which acts as an UV light in this project. Other components include a motor driver which controls the direction of motor movement, and an Arduino Mega to control the whole process flow, and lastly, the power supply and jack adapter to supply 12 volt to the system. This is the flow of the system. Firstly, its motor rotates to move the tray down, then it follows by closing the valve. The pump will then pump water in and turns off after the tank is filled. The ultrasonic cleaner then turns on for cleaning. After it's done, it will be turned off and the valve will open to drain the water. Then followed by the fan and the LED light to turn on during the drying process. After the syringe is dry, the LED and fan will turn off and the LED light strip will turn on for sterilizing. At the end of the process, the LED strip will be turned off. The circuitry drawing is shown on the left, and the pins connected to each component is shown in the table on the right. Most components uses transistor for control purposes, as there is only the power and ground wire on the component. The motor is connected to pin 2 and 3, and the fan is connected to pin 4 and 5. LED strip is connected to 6, and the pump is connected to pin 8 and valve to pin 9. Lastly, the LED is connected to pin 12. The schematic shows the connection of all components. This schematic will be useful in knowing how everything is connected and could help in reduce costs in production, where everything can be connected to a PCB board. As for the budget overview, with all the electrical components used for the prototype, is estimated to be 228 Sing dollars. However, from the electronics perspective, the Arduino Mega could be replaced with AT Mega 2560 chip and PCB board to reduce the cost for approximately 60 Sing dollars, which help reduce the cost by a good 30%. Next, I will pass the time to Hui Jie to talk about the software requirement.
Thank you, Shenji, for talking about the product components. I will be proceeding to the software requirements. These are some of the non-functional requirements that we are trying to focus on to value add our products. Firstly, we want 95% of the user should not have any difficulty to have used our user interface. Next, the delay of proceeding to the next screen should be within 1 second. And lastly, the camera should be able to detect 99% of the syringe being dry. For software specification, we will be using Python 3.8, Tinker for our GUI, Raspberry Pi OS for the communication with Arduino, and lastly, TensorFlow Lite for machine learning with OpenCV. As you can see the image on the bottom right, you could see that the syringe is actually placed with other objects that are still drying. Due to the lack of space, the nurses actually undergo a time-consuming process of drying the syringe. And bacteria may be formed on wet surface, or even worse, the formation of bacteria may also be accelerated in wet cluster. As you can see from this image, that the drying of syringe actually took between 120 to 140 minutes. How do we ensure the syringe is being dry throughout the process? I could have set a timer of 120 minutes for the syringe to dry. However, within the 120 minutes or after the 120 minutes, the syringe might not be even dry. And if I were to set a timer of 140 minutes, the syringe can be dry. However, it might be very time consuming. So with machine learning, we want to analyze and guarantee that only dry syringe is being produced. We would like to also focus on the time spent to dry the syringe and give an estimated time instead of a fixed time. The faster the drying of the syringe, the more syringe the nurses will be able to reuse again. So these are some of the classification that we are trying to focus on. Firstly, it will be wet where the water vapor in the syringe is very visible. Next will be moist where the syringe are actually partially dry. And lastly will be the syringe being dry where the barrels are actually transparent. Next, I will pass my time to Chinkiat to talk more about the final user interface.
Thank you, Hui Jie. Now I'll be talking about our final user interface. For our interface, we build it to be easy to understand and simple to use without the need of any training. This interface will be displayed onto the 5-inch start screen that is attached to the Raspberry Pi. As you can see, from step 1, it shows the welcome screen where you will advise the nurses to place the syringes inside the machine, and then they can click the start button to start the machine. So once they've done that, they move on to step number 2, where the interface will show that it's cleaning the syringes by lowering it into the water and starting the ultrasonic cleaner. So it will also show that there will be a countdown timer, which will be fixed to 15 minutes for this phase. So once this timer runs out, you will move on to the next phase, which is in step 3. So for the drying phase, the timer for this actually varies. because because our computer vision will actually detect if the syringes are dry or not. So let's say if the syringes are still wet and the time is about to run out, our interface will actually increase the estimated time, so that the syringe have more time to dry. So our goal for this is to hit approximately 40 minutes for drying. So once that part is done, you'll move on to step number 4, where the syringes will be subjected to the UV light and be sterilized. So for this phase, we also have another fixed time of 5 minutes, so which brings the whole entire process to approximately an hour. And then once that 5 minutes is up, you actually move on to the final step, where you'll tell the nurses that the syringes are ready for collection. And then once the nurses press the collect button, you will actually reset the machine back to step number 1. So other than the flow I just mentioned, there's also 2 buttons, as you can see. So for the left button is actually the play and pause button, where the nurses can actually pause the machine if they want to. And then on the right is actually the stop button, so which will show a stop confirmation, as you can see. So if the nurses click yes, then the machine will actually reset back to the original welcome screen in step 1. So I'll also be talking about communication between the Raspberry Pi and Arduino. This is actually done using the serial communication by a USB cable connected to the Pi and Arduino. So the Pi will actually send the current phase to the Arduino. So that, for example, in the slide, let's say the drying phase just started. So the Raspberry Pi will actually send a message to the Arduino telling the Arduino that right now is the drying phase. And the Arduino would receive the message and then activate the fans, and it will raise the syringes and activate the fans. And it will act according to the phase. So now we'll be moving on to the demonstration. Enjoy the video. And with that, we have come to the end of our presentation. Thank you very much.